Thank you very much for your kind introduction, and good morning, ladies and gentlemen. Happy to be here. So as you heard, I will talk about our recent results on black silicon photodiodes. Not knowing exactly what is your background, so I was thinking I will very briefly introduce you also the material black silicon if you haven't heard about it. Then another concept that we are going to use in our photodiodes is called induced junction. So I will also introduce that as a background. And basically what it is another way to make charge collection efficiently instead of using external dopants, so we can get rid of so-called dead layer. Then I will show the results, optical and electrical results on our photodiodes. And I also, hopefully I have time to also show our results on how we have applied the same technology to CMOS image sensors. Okay, so let's start. What is the black silicon? So basically the name comes from the fact that it's really black to the naked eye. So if you see the silicon surface, you cannot see any reflections because all the light gets absorbed. And why is that? It's because the silicon surface consists of small nanostructures where the dimensions are below the wavelength of the light. And for example, here, the black curve shows you a typical reflectance measured from the black silicon surface. So basically no reflection in a wide wavelength range as compared to a typical, let's say, anti-reflection coating made by PCVD, which of course can be also minimized, but only for one single wavelength. And then you may know also what happens if the light does not come perpendicular to the detector, but on an angle. So of course, these anti-reflection coatings do not work, but black silicon is good also at very wide wavelength, acceptable. Also all the way to 70 degree. When you tilt your wafer, you see it's also black in tilted angles. Okay, but since it consists of these tiny nanostructures, you may think immediately, okay, but we have an increased surface area, which is not necessarily a good thing for a photodiode because the higher the area, the more you have chances for surface recombination. That's not what we want. We want to have the electrons to the contacts. So we need to find a way to passivate the surfaces. And these conventional layers do not work like PCVD method because it's not conformal because we have these very tiny nanostructures. But you may have heard about atomic layer deposition, which is the method which grows the oxides and nitrides layer by layer. So this is a really nice match to our nanostructures because you can have really nice and conformal coating. And what is also a nice thing about ALD, especially if you do this well-known aluminum oxide deposition, this material forms really nice interface with the silicon because it's really highly negatively charged as compared to, let's say, thermal oxide. So we have also not only a good interface chemically, but also we have so-called field effects. So negative charge repels the electrons away from the surface, and we can have either, depending on the polarity of the substrate, nice accumulation or inversion there. So we can prevent the recombination pretty nicely. There are three different, if we go back to this black silicon formation, so about the fabrication, so there are three different methods how you can fabricate it. We are using all of them in our lab, and we have also made the photodiode out of all of these. So basically using the plasma dry etching, then chemical etching, wet etching, or the laser processing. And today in my presentation, I will show our results on this middle one, so metal-assisted chemical etching, because it's also maybe industrially most viable method because it's very simple. It's just a wet chemical where you put some nanoparticles a few minutes in, and then as a result, you have really nice nanoparticles. And that's already an, for instance, in photovoltaic industry, already in commercial use. So this upscaling is also relatively simple. Okay, with that said, that it's simple and cheap. It takes still some time to optimize. I don't go to the details, but this is what we have done in our lab to really vary the parameters of the MACE solution to tune both the surface morphology good for optics, but also at the same time also for carrier lifetime, so that we don't have this recombination that I mentioned. So these are also like ALD coded nanostructures. what we have measured here. Okay, so this is the background for black silicon, but then the other concept that I mentioned, what we are going to use is so-called induced junction. So we also utilize here the same material, aluminum oxide, which is highly charged. So if we have high resistivity, let's say N-type silicon substrate, we generate really nice inversion layers. So this kind of artificial PN junction, and we don't need to use extensive ion implantation or diffusion to generate also the like a doped region which easily consists of recombination centers. And here's also simulation results showing that we can really make this inversion layer throughout the nanostructures so that we have the PN junction or high electric field inside the whole nanostructures. So this, together with black silicon, we integrate them to a photodiode, and here's just a photo. You can see also how black the surface is, and then cross section of the photodiode that we fabricate. So normal PIN photodiode, but no external doping because of the alumina oxide that forms the P-type layer on top. All right, so let's look at the results of these devices. So for instance, the first one of the main parameters is the photoresponsivity as a function of wavelength. So here I have also plotted the kind of the ideal quantum efficiency of photoresponse, which is maybe familiar to you. So you can see that this is the measured data is very close to the ideal one. And what is important to notice is also the wavelength range, also all the way from the UV to infrared. So basically the silicon band. And not so much work has been done in the past for black silicon photodiode. We have found one earlier work on this using the same MACE technology, which is also very good in infrared, but you can see that if you don't passivate the black silicon surface, well, this is what happens. So really when the light absorbs within the nanostructures, then you easily lose them if you don't have this ALD aluminum oxide passivation. And then of course, maybe this becomes more clear if we plot the same data as an external quantum efficiency, where you can see that we are above 90%, almost in all or around 90% in the whole wavelength range. What is also interesting to look at now is also the kind of internal quantum efficiency, and before that we should look at the reflectance. So I mentioned this is black material, but in our case we made some trade-off, especially in this case of MACE technology. So you can see that we are not 0%, but close to maybe 5 to 10% reflectance in this wavelength range. So there is still some room for improvement. But if we look at this internal quantum efficiency, which tell about electrical losses, there we can see that we are in 95%. So the small loss that we have, maybe 5% from the reflectance and 5% from the internal quantum efficiencies or the recombination losses, but pretty close to the ideal behavior already. And then, of course, another important parameter to look is the dark current. So this is just, we have in the same batch in our lab made planar silicon photodiodes with the MACE technology, because typically what you also hear often is that, okay, but then your dark current and noise goes up. But this is just to show that in our lab, we don't see basically a difference between the dark current between the MACE or planar technology. And okay, this is maybe something you could expect because of the good EQE and IQE as well, so there's no recombination. All right, so I have also time to show these image sensors where we also applied this technology. So basically we took just commercial CMOS image sensors, which are known to have high quantum efficiency, so black curve over there, around 90%, and only thing what we changed here is the front surface, and we basically make them black and then coat it with aluminum oxide. And you can see the red curve over there. So we are able to improve the commercial CMOS image sensor in all wavelength range. Maybe the highest improvement is seen in UV, again, because we are having very good optical properties and passivation properties. So to my knowledge, this commercial CMOS sensors still use these anti-reflection coatings, and especially in the UV, these coatings will absorb some light. So this is causing the curve going down. So this is good now for thinking about the UV. And then for the slight improvement in the infrared region also can be explained by the fact that there is some light scattering from the black silicon. So we can also kind of increase the optical path within these thin layers, which are typically 10 microns, these epitaxial layers. And also we showed that we had the commercial diode and the manufacturer data for the dark current. And then also we're able to show that because of the ALD allox passivation, that's what we believe. This is the reason why we are also able to improve the dark current, so that was reduced as well. Okay, so I come to the conclusion of my talk. So I have shown you how the black silicon photodiodes have excellent optical properties. They don't have reflectance losses. They are able to detect the light in wide acceptable angles. They have really minimal internal electrical losses if the surface is activated well. So we have high internal quantum efficiency, and together the first two, of course, explain the high external quantum efficiency. And also I have shown that there is no impact on dark current or even slightly positive impact. So I would say that at least I was convinced that this metal-assisted chemical etching could be also something to think about in the future for photodiode industry as well. Thank you very much for your time.